I'm an engineer at Apple, and this paper came by because Ted, you guys know Ted, right? So Ted suggested
Yeah,
that
Ted.
we look at in another setting, suggested look at all the NeurIPS best paper awards. So this was I think it was a runner-up or something. So I think there's three, and this is like one of the runner-ups in there. Um, okay, so I think we'll just go very quickly because there's a lot of just um, it's fairly straightforward what they're trying to say, but I would just put the executive summary here. So this is reinforcement learning with verifiable rewards, and that means that for example, coding, you pass unit tests, or you have a math question with a particular answer. Those are verifiable rewards. Um, and then people have been what the paper is saying that doing training, RL training with referral graph improves sampling efficiency. So that means it means that the model will get the answer faster in some sense. That is, you don't need to sample as much to get the answer. And then, but what they really want to say is that doing this kind of reinforcement learning does not expanding the reasoning boundaries, meaning that it's not able to, in some sense, it's not able to explore as well actually as a base model, right? And their contention is that, and what they will show in this paper is that the RL paths, the one that they sample, right, after it actually exists via the base model. What does that mean? It's saying that the base model could actually have sampled that path. It may have a lower sampling efficiency, but is sampleable by the base model. Um, and then I guess they put a little bit at the end saying that distillation kind of like significantly different than RLVR because if you look at number three, it's saying that RL just kind of reinforces what the base certain paths that the base model already knows. So the only way for you to kind of like really sample different paths is by via distillation. That is, you have some way of adjusting what the model can actually look at. So let me pause here. I know that spoke a lot. So any questions about any of these?
I thought that it's interesting that all these claims are made specifically to RLVR, so not regular RL or RLHF.
Right.
Um, Basically, for those that don't know, the difference is probably that you have very binary rewards in RLVR. Regular RL rewards can be more dense. You can have partial progress and stuff. But that being said, just, all the claims here are for specifically RLVR.
Correct. And people try to. I guess the paper mentions maybe in one paragraph saying that traditional RL has shown great strides in like performing better than humans, for example, right? And that's a very different kind of like sampling strategy than what's happening here. So in RLVR, for example, you are basically using the model's predictive model to kind of like sample different paths, and then you using the reward to figure out, oh, this path is better than that one. So in some sense, it doesn't sample like completely new paths. And the way that I think about it is like Fermat's last theorem, right? How Andrew Wiles kind of proved it is because he took different sections of like people thought they were completely unrelated maths and then combined it together, right? That's kind of like how he proved Fermat's last theorem. So what he's saying here, like somebody who is able to like compose things which, completely unpredictable ways, kind of like solves this reasoning problem. And what he's saying here is that, well, you train the base model, it knows the, predictable paths, and it has very little chance of doing something completely random, right? And then the only way to do that is like you provide some teacher which is good at that, right? Kind of like really good at sampling different things. So you're not teaching an old dog new tricks. You may teach that a dog that, oh, this trick is better than that one. And don't try that one too much, right? That's kind of like what you're doing. Okay,
Yeah, I also
so
wonder
yeah, that's
I also wonder what folks think about point three. In a sense, like section 2.2 in the paper, like the random guessing, doesn't seem quite as satisfying, where you just try the base model many, many times. And you try it they actually try it as many as 1,000 times. And by random chance, the chain of thought
Right.
and the final answer could get right. Even with statistical significance 0.01, you get
Correct.
10 of them right
So
just by
the
random
answer
chance.
the answer to that, Eugene, is that yes, they're aware of that. So suppose that you had a give example of that. Suppose you had a multiple choice question with just four answers. Then by chance, you're gonna if you sample it, 100 times, yeah, you're gonna get four, right? One of the four, right? So what they try to do is that to prevent this, and that's where a lot of the I kind of surprised. They actually had to look at the chain of thought through their uh, to actually say that this is an accurate chain of thought. That is, you didn't arrive at this randomly. So they actually did a lot of effort here into kind of saying this was not just a random guess. So I hope that answers your question, Eugene. So yes, they're aware of the fact that if you just like sample randomly, you might guess the correct answer. And
I
actually, they
think
have
what
another. Oh, sorry. Go ahead.
so I think what they were talking about there isn't as much about random guessing. A common problem in some of the reasoning models is that they'll get to the right answer with the wrong reasoning and the wrong chain of thought, right? So
Yep,
it's not necessarily just a random guess. At some level, sure, it's like they've randomly spewed out the correct answer to math or something, but the reasoning is all
exactly.
incorrect, right? So a bit of difference than just like one in four, 25% chance of spewing out the right answer. It's that it's misguided in the sense of all the reasoning steps make no sense, or they're down a path, but then the answer is just something completely different. So some of the like open frameworks for doing foundation model RL stuff. I don't remember which one I was looking at, but I was pretty intrigued by in training, they also check chain of thought, right? And I was like, how are we doing this? Are we just shooting it at an LLM to be like, does this reasoning match this output or what is it? And it's quite easy. There's like quite a few different checks to do it. Not to say that it's not like they didn't
Mm.
put manual effort or they didn't put effort into catching it, but it's pretty programmatic. But it's still like, it's still pretty close stuff.
The other one that they
Yeah.
did mention. Oh, sorry. Go ahead. Eugene, sorry.
No, not to belabor the point, but they checked, I think, like 25 answers. And, spoiler alert, all the majority of the chain of thought was correct. I think 23 or 24 out of 35. That's it. I also wonder what is just the raw likelihood of the chain of thought being correct, given that they sampled it 1,000 times. But I don't have very good priors for this. So
Uh,
that's why it was not very satisfying for me.
the other one that they did point out was about coding examples. So, for example, the three benchmarks, in which is actually harder to guess the correct answer. That is,
Yep.
by randomness, it's actually pretty hard to get the right answer. So, in that one, also via the base model, via this pass by K, they're able to find that there is an answer there. So that's harder to get it right by guessing.
On a
Um,
very, very side note, sorry, last topic. I was playing around with some like MechInterp SAEs, and I was just looking at a lot of chain of thoughts and seeing where answer is derived. And it was basically only in math where after like two tokens, just reading the question, the model already knew the answer for the math. And then everything else could be whatever, whether it's correct, incorrect. It never swayed from its final answer output. And it wasn't the same in code, like even a very basic, like what's Python code to reverse a list? It needed to do reasoning, but this was just like my side project, just messing around. But anyway,
Um, Thanks. So going back to this figure number one, this is, and I'll just go by the figures now. So the main points are here, and we can go about what they actually use to show this points. This more conceptual slide here, in which the figure one, what you have here, you can think of it as a branching of like different possibilities that a base model may sample, right? So, the greedy one would be just like you pick the best, highest probability. You have the nucleus one, which you set a particular threshold P, such as you look at all the possibilities that are within P, right? P meaning say point 0.7, and then anything that sums up to point 0.7, those are valid trajectories that you can go and dig into, right? This kind of nucleus sampling. And so here, I guess just trying to intuitively say that after you do more efficiently sampling, that means that, okay, so the +1 here means that you got the right answer, for example. So RLVR will kind of like reinforce this particular path on the right because you got a reward in it, right? And I think they use a word like sharpening the probability, right? So yes, so you're saying that after you do this thing, the probability of going this right-hand path of those tokens will be increased in probability. You're sharpening that because you gave the reward and so forth. And as the result of that sharpening is that suppose you give another problem B, it is less likely for the RLVR model to actually go to the left here. You see that in the base model, yeah, you still have some probability of going to the left and finding the answer to problem B. But after you did enough sharpening via RLVR, that it has actually, you reduce its capability of going to the left, right? Because and obviously because you did not train on problem B here, right? So you weren't reinforcement learning here. But the point is that well, another point here is that they're claiming, I guess this part three, is that the base model was capable of actually going to the right-hand side, right? Okay. See else here. Okay, I think that's okay. Yeah, we can talk about the number of samples here. So, and I guess this is kind of like they wanted to showcase here. So the yellow, green, and purple ones are different training curriculums for and the black one is just a base model. So, and coverage here is past a case like, so with just one sample, you have very low probability of passing versus the ones which have more training here, they're able to have a higher passing rate, if you like. But as you increase the possibility, that is, if you allow like X number of samples, I guess in this case 2056, you notice that there's an interesting inversion here, saying that the pass rate, it's actually better with the base model as compared with the RLV trained with RLVR models. So there's seems to be like here you peter out in the capability, like you having done mostly going this particular path, you no longer explore this particular ones. And I guess in some sense, let's forget about the passing one. It's comparable, right? That is, at some point, they'll kind of like converge. That is, if you sample enough, you get the same answer as the RLVR. Now the paper obviously doesn't say, okay, how are we going to choose this answer or whatever. It just says that it is within its capability, right? So it's a separate question to say, hey, how many samples should we choose? How do we get to the correct answer? That's not the problem of this paper. Okay. All right. So what other ones? I think they're very similar. So the green here is a base model, and the red one is, oh, sorry, the green one is a base, right? And then you can see that pass at K, it actually begins to, they have the same capability as the RL one. So the RL one again begins with a higher pass rate at K equals to 1. And I think here just showing like difference between different problems and different model sizes and different models. Showing that this phenomenon is pretty much similar, that the base model is able to go that particular path. All right, let's go to the code. Okay, so this is code generation. So the live code bench one, similar. So similar kind of characteristics. And this is just a 64, right? That's okay. All right, so visual benchmark, they all show very similar things. Now the visual one is kind of interesting. So what's interesting here is like it passes, oh, sorry, question. It passes much earlier. And let me see, did I forget like why that's the case? Let's see, is it just because, let's see, right. So now you gotta include visual information, and now you're asking, can the base model kind of like figure out how well can you do with RL versus just the base model. So I wasn't exactly sure like whether I got a conclusion. It feels like it feels like they just, once it feels like the RL one, you kind of earlier, it seems like you need more. It's kind of surprising that, you just need two samples with the base model. So in this case, or maybe like 32 here, right? So, but it's still much smaller compared with the other ones. And I guess my question is like, why isn't the gap larger here? And yeah, so I'm not sure I got a conclusive answer from reading the paper. I think they said that in the visual one, you have more ways of interpreting an image, I believe. Okay, what's this one here? So this is accuracy, so probability of accuracy distribution shift. So what does that mean? So let's take a look here. Can I make it smaller? Oops, nope. Okay, so it's a histogram, and it's a histogram of like both the base and the RL. And what you want to see here is like just roughly what it's kind of saying is that if you look at things which are low frequency here means like how often you get the given a particular set of problems, and like if you have what the let's see so how accurate you are. And the distribution here is like you can see that you have high frequencies here when the problem is kind of hard for the base model, right? So, and then as the problem is kind of like easier, right? The RL kind of like picks up that better over here. Now, it's interesting to me that I'm not sure how much to take this tail here on the RL one. But I think the distribution shift that they're basically trying to say is that is actually what we're trying to say. It's sort of similar to these pictures here. That is, as the problem becomes kind of like harder, if you like, and that's going to the left, that the base model is kind of like sort of slightly better. That's why I was kind of like interested on this last point here. It's kind of like weird what you get this last one over here, but overall is doing better, and that has to do with, remember, that branching diagram that we said. So there's a distribution shift here with the problems that it has not like sampled before. Sorry, is that maybe I didn't do a good explanation here. So this is kind of like saying that for problems which the RL is able. Oops, my mouse died here. 1 second. Oh no. Oh no. Okay, here we go. So it's kind of like saying here that the RL1 kind of has better sampling efficiency for the problems that it kind of like knows, but doesn't do so well for the problems that it doesn't, versus the base model one has better actually sampling efficiency than the RL1 for problems that it does that were harder. Okay.
This chart is so interesting, right? It shows you that RLVR
Yeah.
gives you like gain on the top two accuracy intervals of 30%. But then it is worse than the base model on the remaining 70%
Right.
of the intervals. But that's it. It still achieves higher pass at one
Yeah.
on the broad coverage of data. So it makes me rethink how I think about RLVR and how it contributes to model intelligence.
Right. I think it's more about like a use case, right? So like if most of our problems that we care about we can live with this efficiency, great. But if we really want this stuff to like solve hard problems, I think the point of the paper is like don't rely on RLVR, right? It's not doing what you
Yeah,
want, expect it to do.
exactly the diversity trade-off, right?
Yep.
Like being
Mhm.
correct very quickly versus the diversification.
Yep. Yep. Cool. Right. So, oh, okay, this perplexity one. So let's see. Do we have everybody's aware what perplexity is? Um, so let's see, maybe I have a demo here. So make sure people know what perplexity is. See if I can bring it out quickly enough. Oh, here it is. Okay, so I have to share something different here. see, how do I change my sharing? I have to stop share again. 1 second, guys. Okay. And I'm sorry, people here are probably very aware of perplexity, so this is kind of just a mute point. So suppose you had like uh, you're looking at a particular trajectory, right? So in this case, I was looking at the trajectory with like 5 tokens, and you have probability for each of those 5 tokens, right? So suppose that you just keep the other tokens the same probability. And then here, I'm just going to adjust the probability of token 5. Right? So this is just probability. So I just, out of a trajectory of 5 tokens, I'm only adjusting the probability of token 5 and what happens on perplexity, right? So here, probability of 1, so this is the highest one. So it gives me like an average around zero point 0.9 of these 5 tokens. So you can imagine that the other ones were some were about 0.9, some around 0.8 or so forth. You do the average of that, you get around 0.9, right? So what happens if I just change that particular probability of this token as I go? Oh, this is, by the way, the blue one is the arithmetic mean. That just average probabilities. And then here I'm looking at the geometric mean. That is, I multiply the probabilities and the square root of 5 in this case, right? So that's essentially perplexity, the one on the orange one. Basically, it's a geometric mean, essentially. So what happens when the probability of token 5 goes like really low is that it actually is much more sensitive. You see that the impact of that token going, to very low probability or 0.1 is actually much larger than the arithmetic mean because you have the other 4 tokens which were given, the arithmetic mean some weight in here, 1.75. Basically, you're zeroing out to that fifth token probability, which has a much more drastic effect, right? Because that's a geometric mean. Basically, if any particular token on my path has low probability, that makes my perplexity to be pretty bad, right? Or sorry, I should say is that the other way? So it means that that probability is actually pretty low, right? And perplexity is high. So it's actually the opposite. So high perplexity means that it's low probability. Low perplexity means it's high probability. So okay, so in this case, you're gonna have very high perplexity here because the probability is very low. Okay, going back to our slides. So it's clear, everyone. So perplexity is just geometric mean of the probabilities of the tokens and trajectory. Sorry, share again.
I actually thought you were going to explain perplexity itself. I think one of the interesting things that I would offer to that I've observed is that perplexity's number has absolute level meanings, which is very interesting.
Hmm.
Uh,
You,
do you know what I mean by that?
yeah, you want to share that with us? Sorry.
I don't have a source, but like I just anecdotally observe when people who train LLMs a lot, they're like, "Oh, my perplexity is under 20." And then they're like, on your last
Hmm.
chart, you had like perplexity 4.6. I was like,
Right.
people would instantly look at that and be like, "It's too low." And I'm
Huh.
like,
Oh, has some sense of what that number means, right?
yes, yes.
Yes.
Like
1 second.
English default irreducible perplexity is like 8. Like,
Oops. Sorry, let me get my sharing again. Somehow it stopped
So,
again.
is
so quick note, perplexity is absolute on an absolute scale, but it does depend on the corpus.
yes, yes,
So in your
but yeah.
corpus, you can have a lower perplexity. Yeah.
Okay.
It's just interesting
Oh,
that
sorry.
people use shorthands like that to like talk about their training progress.
Okay. So what are we comparing here? It's a perplexity. Recall again, perplexity means what? The higher the number means that you have that lower probability of stuff, right? And the lower number means that you have oh sorry, says the opposite again. So high perplexity, low perplexity, high probability, right? Okay, so hopefully I said it right. Okay. So what are we comparing here? We're looking at the perplexity distribution of responses. Okay. And let's see. I forgot to see what the left and right was. Okay. So the y-axis is again has to do with frequency, and the perplexity score here is going from I think it's just different PPLs. So you have the base one models and you have the RL. This doesn't look. right to me. Okay, right. So I think you have four basically charts here of the distribution of perplexity. This is for the base model, and this is for the RL. I forgot what GT is here. Yeah, let's see what the GT is. I've forgotten.
Is that ground truth?
Yeah, okay, the ground truth. Okay, I think you're right. Yeah, ground truth. Correct. Okay, so what is this saying here? Okay, and if we look at the, oh, I guess I have to interpret what this base RL is. Sorry, I've forgotten now. I get my paper out. Okay, sorry guys. Just go to that figure. I forgot
So I think
what
the
those two are.
subscript on the PPL is which model you did for inference, and then in the parentheses is which tokens you were checking if it was high or low probability of. So the
Oh,
one on the
okay.
right would be using the base model and using the ground truth answers, what was the probability of each token averaged, and so on
Okay.
and so forth.
Okay. So, well, so the ground truth is kind of interesting because it's saying that the ground truth is low probability, right, on the base model, right? That's what it's saying here. The perplexity is kind of high for the ground truth one. And I guess y base as Seng's test. So y base then that corresponds to the perplexity for just the answer from the base model itself. And then it's showing that the RL, and so this is a good one. So it's saying that the RL one, so whatever the RL model gave versus whatever the base model has actually the same perplexity for the PPL base, right? That is, the base model for that particular for this particular pass show the same perplexity, which kind of like reinforces what they're saying. That is, that the base model is able to sample that particular path from the RL one, right? Now, if you look at the perplexity for the now, why is it kind of like really low? Why is it low perplexity here? Because this is very highly probable, right? So it's that's what the so this means the perplexity for the RL model that has been trained with RL for that RL path is actually very high. So that's exactly that sharpening that we've been talking about. So that particular YRL path, the one that from that tree that goes to the right, has very high probability. That's a sharpening going on. But it's saying that that particular path has, is sampleable by the base model, right? That's gonna, and I wish like uh, I knew what this number is exactly mean, but whether or not that's highly probable or not. So very interesting. So any questions about this? Um, Okay. So I think it just reinforces their claim that the RL path can be is within the base model one. All right.
I have a
Okay.
quick
So
question,
sorry. Question.
Frankie.
Yeah.
I'm actually curious what you guys read on it. Is the YGT is actually the result from O1 model, according to the paper. And the perplexity actually looks very different as compared to the three other ones, right? So which means that probably because the O1 model was trained in a very different methodology as the peer RLVR approach. I don't know any more reason to this.
Actually, let me maybe sorry, I
Because the
forgot
complexity
that.
is actually high. In a sense, it's actually
Low
not,
probability for, yeah, not
yeah.
likely that is. Now the question
Yeah.
is this YGT one, is that actually
It's the paper
correct?
says it's from the OpenAI's O1 model.
Which means that they did a chain of thought on this or one model,
Yeah.
or and that because I sorry, I've forgotten, but does that mean that it actually achieved the answer on this O1 model, or is it
Uh,
just like like
I
they gave
think
some
they,
prompt?
yeah, this is they let the O1 model generate eight responses and then
Okay,
denoted as YGT. I didn't
uh,
expect to say whether it is a correct answer or not,
okay.
just eight responses. Yeah.
Right. So I think it just means base. Means like they just need some baseline for between this RL and they just want to compare. Well, actually, if they really wanted to use base, they should have a YGT on the PPRL, which they don't.
Yeah.
So that's kind
Yeah.
of like bad. So it's not the true
I,
baseline to me. It's kind of
Mm.
not useful.
I, I kind of thought of it as, comparing the Quen 7.5 versus GPU-01. Like, what is the difference in perplexity between two different reasoning models? Like let's have that comparison. And then here's what's the difference in perplexity between a base model and an RL model that is exactly the same base model. That's kind of I thought about it. That's why it's compared against the base. But maybe I'm reading too much into this chart as well.
If
Yeah,
you
go ahead.
open the paper, they have a paragraph around it on page number 8, or actually, just a minute, page number 7.
7.
Yeah.
Um,
Actually, come to page number, yeah. I mean, it's page number 7. There's a perplexity analysis. There they have a very good description of what exactly they're doing.
okay, let
Like,
me share. Yeah, let me share that. Sorry. We're on the same page.
That is, it explains what they're doing, but it doesn't quite explain why they did it.
fair. That is in the appendix. Or rather, no.
So I don't see the so right. So they well, yeah, they don't say anything about the why they use the GT, right? So kind of unclear. Yeah. Yeah, because I think the comparison is mainly between the YRL and the Y base one, I believe. Yeah. Okay, let's continue. All right, next. All right. So here's this distillation. Okay, so and this is kind of a little bit. So I think they began by saying, like the base model is just can get that good result as the RL one if you give enough samples. And now they're kind of like breaking away a little bit and saying, hey, so how do we get even, how can we improve the performance beyond the base model? And the only way to do that, they seem to claim, is to say you need to change the behavior of the model itself. And to do that, you need to do distillation that is able to explore, different paths, right? And so this is kind of like the distillation part of things. And the distill here, I guess you can see it's above everybody else on its on its pass rate. So meaning that you essentially enable it to explore different paths, and therefore it has better pass rate. Okay.
The folks
Anything
think
else?
that
Yeah.
there's a confounding effect here, whereby they use a distilled model trained via completely different methodology. It's just off the shelf, right? And I can understand why they do that, because they just don't have the no effort and compute to try to do it again. But I wonder if the distillation approach is using different data, different level of compute, different algorithm, and therefore the reason why the coverage is higher may not necessarily be due to the distillation technique, but also due to other possible confounding factors.
Um, so let me make sure, Eugene, is that was your question, Eugene? So
Yes.
I think in some sense, yes, you're definitely doing SFT on a more powerful reasoning model. And then maybe you're trying to kind of pick that out and say what part of it like enabled it to what part of it improved? Is that kind of your question? I just try to understand.
I
Basically,
guess
yeah.
I guess the green line and the pink line,
Mhm,
they did this themselves. Right. That is straightforward. The purple line, I'm not quite sure what it is. But the black line, the
mhm,
distilled model, I know they took an off-the-shelf model.
right.
Now there could be many different variables between the green, pink, and the black line
Mhm,
beyond just the technique, right? It could be we don't know what kind of distillation data, what kind of distillation algorithm was used for the distillation model. When I say algorithm, I mean like the loss function, right? And what kind of
mhm,
compute it was trained on. So all these things could contribute to the difference in coverage beyond just distillation, the technique itself. So I wonder if
mhm,
this example here is just goes too far to say that distillation actually outperforms RL when
mhm.
there could be many other things. There are many other things that are changing. Or
So
maybe I'm again reading too much into this.
yeah, I'm wondering, like maybe I'm kind of like and maybe interpreting incorrectly too, in the sense that I was just thinking that what they did is they picked very good long chain of thought reasoning traces, right? And then this SST on this into the base model, right? And then they showed, okay, how much did it improve if I do this? Okay, I think that's all that they did. But maybe even that simple process may have a lot of different effects. That's kind of like hard to say why did it improve. Maybe that goes to your point there, right? But I think that right, they just picked some off-the-shelf model, like you said, and then
Yeah.
added this extra training step to it, right?
No, actually, they just used DeepSeek R1 distilled Quen 7B and
Mhm.
plotted the black line.
Yep. Yes.
So they didn't do the distillation themselves. So it's not sure. I'm not sure what data. If everything was constant other
Oh, I
than
see what you're saying.
distillation.
Uh-huh. Got you. Yeah,
Yeah.
you're right. They didn't distill themselves. Agree.
Uh,
Which will be
would
better. Yeah. Mhm.
what would you expect them to do? Would you want them to try, like, because this is all about RLVR, right? So would you want
You're
them
right.
to do distillation on the same data that they did the RL on?
That would be nice. Keeping everything constant, but just changing the distillation, so that we can make it clear that it's an ablation. I think they didn't quite present this as an
Yeah.
ablation study either. So, I mean, given the limited resources and compute, but I also don't know it. I also wonder if it's too much of a stretch to say that distillation expands the reasoning boundary,
Mm. Right.
because
So
we don't know. Yeah.
can I jump in? So Eugene, I
Please.
think the point they're making is not that distillation is guaranteed to be awesome. Uh, it's just that distillation from this one curve shows new capabilities were trained into the model. Whereas the whole point of this paper is that RLVR does sharpening, but it doesn't ever give you a new capability. So there's no guarantee that if you do a distillation, it will be great, but it's possible for it to be great. Whereas they're saying effectively RLVR, it's impossible for a base model that cannot solve like hard math problems. No matter how much you do RLVR, it'll never do a theoretical proof that the base model couldn't do.
Thank you for reminding me of this, Ted. I think you're right. In a sense, the base model here is always the same. It's always a Quen 7B.
Right.
Regardless of what the distillation, the base model is always the same. But at least we can say the distillation, the graph is always above, even though the base model
Yeah,
is the
and
same.
so that
So
would be
so
maybe
there's some nuance there. Yeah, you're right.
yeah. So that's credit to DeepSeek. They did a good job distilling, and so your mileage may vary, but they're just proving that it's possible to get
Mm.
better from distillation. Whereas they're saying RLVR, you have a glass ceiling. If this base model was never going to be able to prove Navier-Stokes, then no amount of RLVR will get you to being able to prove Navier-Stokes.
That's true. Thank you
But
for clarifying that,
distillation
Ted. Yeah.
could theoretically, not that it will, but
They demonstrated that it could from the same base model. Yeah. Whereas
But
RL, yeah.
is it not generally true? Like, if you have two models, one you have pre-training to say a 7B, one you have a 72 billion base model, and you're distillating it to a 7 billion model. The resultant distilled model would always be smarter than the one that you're pre-training to the same level.
I think what they did here, and correct me if I'm wrong, is the distillation is on the same Quen 7B. They took DeepSeek R1, they got the chain of thought, and
Oh,
this,
so
yeah. So fine
is
tune
it
on top of the Quen 7B.
so is it online distillation? Like, I mean, I'm curious about.
yeah, so the authors didn't do the distillation, but they started with the same 7B model that DeepSeek did.
Yes,
So hypothetically, if there's no unknowns, they had the same base model as DeepSeek, and they're saying DeepSeek's model got some new capabilities, but our
Yep.
RLVR on the same base model
Right.
didn't get new base abilities. It just got sharpening of probabilities on problems it could do.
Correct. Um, so right. I think they did mention something else. So I think we all agree that they did the red line, right? They did their own experiment. And they began with a base model, which is a green. So the base model is the same for the same green one, either for the black one or for the purple one. They mentioned specifically that they did not do any specific SFT on their model, that they just used RLVR to kind of like improve whatever this green line is. And yeah, you get this improvement, that is, you get more efficient over here, right, at low K. But then they're saying that that itself does not allow you, just pure RLVR does not allow you to go up to the black one, right? So that's pretty clear as well, right? So you have to do something else. Definitely just pure RLVR on the base model doesn't get you to the black one. Now, we can make many arguments. Well, did they do a good job or whatever? So they're gonna say, oh well, we tried all the different recipes for doing RL post training, and it says similar results because they all will show that the green one eventually after large cascade will never go up. You have this issue at the right hand side. It never goes beyond that, and that particular pattern is true, independent of the RL algorithm that they have used.
Yeah, when I was reading this section, it made it seem more like distillation is a form of knowledge transfer. So if you have a bigger same family model, it can directly transfer in new knowledge, but RL directly can't, right?
Right.
You're only doing optimization of your current knowledge. So if you think of like
Yeah.
pass at 1024, you can re-optimize what, let's say there's a 1 in 1,000 chance that it knows something, you can make that process more likely. But distillation, you can directly transfer in new knowledge, right? If you have zero shot at ever answering something, you can train it in. Now those are both very extremes, right? In all reality, like the pass at 128, is it probable that the model really knows that answer, or it's just sarcastically guessing the right answer and you're making it more probable with some reasoning in there? More likely it's the latter. But either way, if the model cannot output this answer at all, you're
Right.
not training any new knowledge in with RL. But with distillation, you can directly transfer knowledge in. That was the difference that I saw.
Yeah, going back to this conceptual slide here, the base model has this tree, whatever, right? The RL will reinforce paths on this tree, and distillation will give you new paths which are not in this tree. You can think of it that way, right? You allow it to explore different paths that it never was able to, and that's
Wow.
the main difference, right?
Thank you for that explanation, Vibu, frankly.
Okay, let's see. Think we're getting close to conclusion here. Yeah, this one again, the same thing here is just about the different R algorithms have all the similar pattern. Again, the green one is just the base model, and they never go like at the high K pay pass. They don't go above it. So independent of what we just said, right? They make a big deal of this efficiency gap over here, but yeah, I think the lower efficiency gap is obviously better, but and what they say is that yeah, you have some variation depending on the different algorithms that you use, that the efficiency gap is kind of smaller, but I guess they don't go that deeply as to why you have these differences here. So we'll just leave it there. Okay, and I think that's it. Yep. The appendix has basically similar kind of curves. Oh, there's one thing on the appendix that I should point out. Let me change that, which I thought was kind of interesting, but not a big deal. Let's see. Sorry. I always kind of like lose my Zoom stop share. Okay. Okay, and let's share again. Where's my Zoom share? Yeah. Oh. Okay. And I wanted to share this here. Okay. Okay. Yeah. Just one minor thing that I thought was kind of interesting that they did. And we can go for questions after this. Right. Yeah. So this is just more experiments that they did on the appendix. So I don't think that there's they did include the KL divergence terming here. Yeah, and this is pretty much the same. So the only new thing that I saw here was like, how do they do this pass by K estimation? So that was kind of interesting. So, what does it mean, pass by K? Sorry, we didn't like really talk about this. It means that you sample K times, and then maybe within this K times, you actually get the right answer, right? So pass at K means that you actually got the right answer after you do K samples. But they're saying that, well, if you do this, like just directly computing this, it can lead to high variance. Okay, so what do they actually do? Well, obviously, you actually don't just go by K. You actually sample much more, a larger number than K, and then you count, and then you do this estimation based on that. So it's an estimate to the past over K, right? It's an unbiased estimator of that, because otherwise you get too high of a variance. Yeah, not a big deal, but it's more expensive than what you think. So if they did like 128 is your K, they probably did a factor, I don't know, did they say here how much? Yeah, they did almost like a factor of 10, right? Above. Maybe, yeah, I think they did a factor of 10 above of what you actually need for the K, to lower the variance for the estimates. So it's pretty expensive, all the stuff that they did here. Yeah. Okay, let me stop. I think that's it from presentation. Guess have questions. Oops. Up here. I'll just leave the paper open in case people had questions about different sections. Okay, no questions?
Yeah, overall, great choice of paper. I didn't actually read this or hear about it before, but it's good to know that it's like a very nice self-contained thing, and yeah, it's very well covered. Everyone had good questions.
Yeah. So thanks for that last bit about the pass at K math. I never thought of it that way. It makes sense actually. So I had a question regarding this paper and why they didn't cite another paper, which is the Pro-RL paper. I don't know if you're aware of that one. So it's a paper where they show that actually RL can work if you train long enough. So what they do is they train for around 2,000 steps, and they show that for some tasks, actually RL goes beyond the pass at K improved efficiency, and that in those cases the base models actually learn new capabilities just from straight RLVR. So I'm curious why they didn't talk about that paper.
Can you post that paper for us, Ta?
Yeah, sure. I think it was a paper from NVIDIA. I'm not sure. Yeah, NVIDIA. Where's the chat? It's here. Oh yeah, thanks,
Thanks.
Vibu. Yeah, and they have very similar graphs. For some tasks, the graphs look very similar to today's paper, but for some others, they are. I can maybe share my screen and show you.
Yeah.
I think just quick answer by the way, this one came out before that. Like the
Today's paper?
first, yeah, the
Yeah, it's
first
April.
iteration was April.
Yeah.
But
Oh, that makes sense then.
I think the other one might have also been before May, but at some times like these are written a little earlier before than they're posted, right? So I'm
Yeah.
sure a lot of this work and testing was done in parallel.
Okay, yeah, that would make sense.
The other thing with the Pro RL, I'm not sure how much of that is purely focused on RLVR versus just traditional RL as well. This paper goes out of its way to specifically only focus on RLVR, right? So it's just something to know.
So what do you call RLVR in this case?
In this case, RLVR is RL with verifiable rewards, right? So it's not RL, it's not RLHF, it's not like RL in like robotic simulations where you have partial rewards.
Yeah.
Typically these RL, yeah, this is that type of RL.
Yeah. So in the Pro RL paper, they do the same. It's RLVR. They use
I
like
see.
variants of GRPO and DAPO and stuff like that. Yeah, and it's they do that on tasks that require reasoning, like math and other like reasoning types of problems. And so for some reason I can't share my screen. I don't know why. So sorry about that. But yeah, basically if you go to the paper and go to, I think it's on page 7 of the paper, you can see some plots that look very similar to what was on today's paper, and some others that actually show that for some tasks, even at pass at 256, the base model can't reach the RL trained one, and there's a gap. So yeah.
Do you want me to share the paper? What
Yeah, go ahead,
page are you
please.
trying to talk about? Sorry.
7.
7. These?
Yeah, these ones.
Do you want to explain what we're looking at?
Yeah, sure. So there are 3 lines, 3 rows, and so these are the different. Each plot is one different task, and you can see that, for example, in the very first plot, it's on a math task. The base model is the blue one, and the final trained model is the green one. And you can see that at pass at 256, the base model is actually better than the trained model, which is a similar situation to what they show in today's paper. So that's the first case, and they show that especially for math tasks, that's what happens. But for other tasks, if you go to the last row, you can see that the base model, no, the last row.
The last row, sorry, here.
Yeah. You can see that the base model, the blue one, never reaches the green one, even at pass at 256. And especially if you go to the very last plot. So for this special task, they show that the base model never succeeds, even at pass at 256, while the trained model is almost perfect.
It is perfect, but very cool.
Yeah. Well, it is perfect.
Do you know what this task is?
The
Dice?
task. Yeah, dice. I don't remember exactly where it is.
Interesting.
Yeah. But it does require at least 2,000 steps, which may be expensive. And this is a small model. I think it's 1.5B. Yeah.
Very interesting.
Someone is asking if it works for 7B. I think in the paper they say that they haven't tried to do that because obviously it's very expensive. So that remains unanswered for now.
Quick comment. I don't know this paper really well, but looking at those figure 4 charts on page 7, on some of them the blue line isn't plateaued. So, right, if you look at the middle one far right and the first two on the bottom row, and so you can't say that the orange and green are above the blue line until the blue line hits its maximum. Right? So like Swix kept pasting like here's the crossover point, but until you see the blue flatten, then you don't know if there might be a crossover just further to the right. Does that make sense?
Yeah, that makes sense.
This is hitting full accuracy past at 256. So basically, like, if you go past 256, that was the other thing in the other paper. They did go more than past at 256, right? They went to over 1,000, 2,000. Does this just really slowly hit 1? Like, is this 0.97 already in the model?
Right.
They
That's what I'm
didn't go
saying.
far
If you
enough
didn't
to
pass
check.
that 1,000, 2,000, 8 million, does the blue line eventually get to the same 0.979? But it just is really, really rare, really hard to sample it. This one definitely looks like the blue model just can't do it. So
this is kind of the alternative to that, right? Like, this does show something. I don't like 0. Well, I guess it degrades slightly, but anyway, this is kind of the contrary case, and I think you can start to extrapolate out on some of these. I think this is kind of tapering off, but yeah, I mean, if you keep going, does this reach 200? Potentially.
Yeah.
That's like the main
Right.
claim you
Yeah.
really have to see in this, right? Like this is already at 90%. They're pushing it to 97, but if you give this more shots, does this line just continue out to here?
Yeah.
Ooh,
That's a fair
incorrect.
point.
Yeah. And then the
Yeah.
lower right corner, it is a strong case, but I don't know if that's just a fluke where the model just
Uh,
happened to be really bad at this and
yeah.
it got some nudge, you know.
They do another experiment on another task that shows the same behavior. If you go down, yeah, this one. This is another
Which
one.
one? This one?
It's a boxnet, and
This one?
not this one, the one above. Yeah, this one.
This, oh.
Yeah, so this is
Yeah.
another one, and yeah, they show the same. So,
Yeah,
and
this reminds me of like, some of the Arc AGI puzzle tasks and stuff where like the ability is not like constrained because it's too difficult. It's just stuff that you would never expect to see. It's not in the probability distribution. So, pass at 1,000,
yeah,
you'll probably never get one right. But that doesn't mean that this thing can't learn to play a basic game, right?
yeah,
So I
yeah,
think the
absolutely.
capability is in there. It's
And
just that even in random noise at 1,000 steps, you're not getting this.
yeah, and the point they make for this one is that this particular task was never seen by the base model, and that's why they get this behavior.
Yeah, I think this just falls into some, like even this dice one, right?
Hmm.
Our benchmarks don't encapsulate proper coverage of model behavior, right? Like
Hmm.
if you were to augment this benchmark and task slightly, I'm sure a base model has some performance. It's just like the number of steps for this is straight zero, right? It's
Yeah.
in the other paper, we talk specifically about math. And in
Hmm.
math, at a certain number of steps, you'll eventually guess the correct answer, right? So there's
Yeah,
some
yeah,
baseline performance even with all wrong reasoning. In logic games and stuff like that, you're just never going to output the right path, right? The probability becomes too small. So it doesn't necessarily mean that the base model is like really zero. If you were to decompose this task down, like can you solve 5% of the game? It might have different numbers, right? But
mm,
this is just me speculating.
yeah. No, they actually make they arrive at the same conclusion in this paper. So
Yeah, yeah.
It's
I
a
mean,
short one though.
nobody's saying that you can't make a model do something it has no clue how to do. But if we're really trying to test like chain of thought reasoning, right, then I think that you want the model to have some capability in the base model to measure against. If it's just flat out zero, like, you
hmm,
know, like, I
yeah,
don't know, if you had a model that was trained on just English and somehow really, really, really tuned to be only English, and you gave it some French text, then it might just be zero, right?
yeah,
Nobody's saying that
yeah,
if you do some fine tuning on French that it won't do better, but like that's not really the point of RLVR, I don't think.
yeah. Mm,
I think Ted, we were talking about the other paper about how KL divergence kind of like pushes it into this um, whatever it was its parameter space, kind of don't deviate too much from the model. So what they did on this this pro arrow thing, they're aware of this entropy collapse that is things are sharpening, and what they did there, two things. They kind of like softened that KL divergence term, and they also kind of make the clip, the clip stuff, which doesn't allow you to go beyond certain things. They made to be more dynamic, but I think that's all that they did like differently in terms of their RL recipe. But it feels like to me like you're training on different problems that in some sense kind of going back to the dog analogy, right? Yes, if my dog, I'm not training new tricks on it, then it kind of like doesn't know how to do something new. But then if I'm feeding it like new curriculum to it, like new ways, new problems for it to solve, maybe it is learning something from just like giving it new problems, right?
Well, I mean, I have a very simplistic way of saying it, which I don't think people should take overly literally. Okay. But if if the RLVR process looks like sample potential outputs from your model and then bump some up and bump some down, doesn't it kind of intuitively make sense that you're only going to get answers that the model could have said in the first place because you only sampled from things the model could have said in the first place? Now, obviously, don't take that too literally. There is some way in which it could start to, I don't know, grow beyond its bounds. But in a simplistic sense, you are just upweighting things it already said when you run RLVR. Whereas when you do SFT, you're doing traces from some other model. You're giving it out of distribution text that you're training it on. So whether you used SFT or some other algorithm, it is still a OOD training set versus RLVR is fundamentally a my distribution training set. And the same is
Yeah, I
true
think
for RLHF and other stuff too. You're supposed to use, in distribution data.
I think the interesting thing in like most pre-training foundation model papers we see, like even with DeepSeek, a lot of them kick off their RL with the cold start SFT, right? So before they do any RL, they first do a cold start of SFT. And that probably speeds up and solves a lot of this stuff. But back to your original question of why the paper didn't bring up why it didn't talk about this. So it's actually the other way. This paper is directly responding to the other one. So in the intro, it says a fundamental question remains under active debate within research community. Does reinforcement truly unlock new reasoning capabilities? And then recent studies 13 to 50 argue for the latter. So this is actually directly citing the paper we just read. So this is the one, does RL actually incentivize reasoning capacity beyond? I guess there's two more papers that also they're refuting against. So, there's two more here that people could dive into if you're interested that are on the same topic. RL post training amplifies behaviors learned in pre training, assessing diversity, collapse, and reasoning. But you just kind of had it the other way. So this paper is a response to the one we just read. That's why that one doesn't respond to this. So they're actively trying to claim the opposite. But
Ooh,
yeah,
okay.
cool more papers. Yeah. It's
That
right
makes
there in the
sense.
intro.
Thanks.
This is the exact one.
Yeah.
If we also go to the paper, sorry, yeah, if we go to the paper today, there is also an element. I was just reading the prompts that towards the end that the model doesn't is asked to like reason step by step, but there are no thinking tags or anything except for code R1 prompt. That might be something.
Do you want to say what page? I can pull up the paper.
28.
28. Here?
Yeah, 27 essentially.
27. Yeah, okay. Prompt templates.
It says please reason step by step, but ultimately all it's asking is just give the answer.
Yeah, I mean that's the thing with RLVR, right? You're doing outputs of your reasoning and you're giving your final answer. So it's boxing its answer. Part of that is like they want instruction following, like you'll lose, you won't get your reward if your answer is not boxed and stuff. But I think while I was pulling it up, I didn't hear the first point you were trying to make. Like the base model wouldn't be able to do this, or what was the point?
The point being that if you like specifically go for reasoning, right? I mean, like for example, the code R1 prompt. Sometimes the behavior changes because there are it can be arguably said that in the thinking part of it, the model generalizes from what it already knows. If you have a simple RL, for example, how Sonnet 3.5 was trained, or Kimi uh, K2 was trained without the reasoning aspect. They also used RL, but in that regard, it probably is more plausible that the model just sharpens the reasoning parts. But once you start training with the thinking tags and all, that probably means that the model can think more and can generalize. That's the assertion.
I see. Yeah, I think that's a fair assertion. When you allow the model to think, it can think more and generalize.
Can I ask, is there a reason why you think begin think and think tags change what the model is able to do other than just delineate it and make it easier for us to hide it from the end user if we don't want to show them all the thinking in between?
Uh, One of the reasons, and I mean, it's obviously debatable at this point because we don't exactly know. But one of the things that happen is at a very high level, the response length is very high in terms of when you're asking a model to, generate those think tokens and then actually go on and solve. Essentially, from what I've seen, this paper has around like 1,000 or 2,000 response length, but usually you get to like 8,000, 10,000. And the more you ask a model to, think before, it essentially is generalizing from the priors. So in that way, a model can compose from different concepts. It can like, go around it. Uh, and then it can probably solve the problem. Because one of the other question that I have is that if this paper is like 100% true, are OpenAI and others betting the house on the wrong thing? Because if these guys can figure it out, it would have come up in their studies maybe a year earlier.
I have two questions. Also, I know we're running very long over time, so if anyone needs to head out, thank you, Frankie. I hope we're not keeping you.
We'll
Really
be quick.
good paper coverage. Yeah.
Yeah.
Uh, Um, on that topic, one, there's quite a few benefits for adding think tags, right? So if you want hybrid reasoners, if you want to force the model to do thinking and enclose it in thinking tags, also in some of the RL policies, you're rewarded for formatting. So if the thinking tag is not there and you're still thinking, it helps with training where you can penalize that. And then on this question of betting on the wrong thing, I think the thing you need to remember as one of the takeaways from this paper is that all this stems from a good base model, right? And OpenAI and those they're the real ones training massive base models, right? So I don't know how much they're doing wrong if they have really good base models. And you clearly also need this, right? Like you can do a lot by reorganizing your RL.
So my take on the formatting of reasoning models is that it depends what you are training for. So, for example, if you're training just for in the context of experiments or in the context of producing a paper to test stuff, then I don't remember in which papers I've seen this, but they actually show that the simplest the format, the easiest it is for the model to just use it, and it's also easier to parse. But then, if you are training a model that's going to be as a company your flagship model that you're going to expose to consumers, then it makes sense to have a format that you can easily parse, for example, to either hide the chain of thoughts or maybe allow the thinking tokens to be toggleable, collapsible. And so, yeah, I think defining the right format depends on what the end task is. I don't know if it makes sense.
Hey guys, I also have one question. I just put on new paper like from the CMU. I think on December they also try to show they discuss a capability. So when the RL actually can outperform the base model, so in what case actually cannot. So it was a very interesting paper, but like their result is only test on very small, like 500 million size of a model. Also, I think Taha also showed is like 1.5B. I do have the question whether this we're observing that some RL actually can be outperform beyond the base model. Is that only showing small size model? Because I also see like so today like these like presentations paper, we also see very similar paper with similar result in other lab, but also the show is more of a 7B or 14B. So I'm wondering if there is a difference between small size model to mid size or large size model for RL. So any people have some comments or idea on this one? Yeah.
I haven't seen any model that does that, any paper that experiments with larger models. And my intuition is that if small models are already good with at pass at 64 or 128, then I would expect that bigger bigger models would be even better, and it would be more challenging to show that RL goes beyond the pass the base capabilities, the capabilities that already exist in big models. So yeah, that's maybe why we haven't seen it yet.
I think some of the foundation models that we see, those papers that actually end up doing RL on different sizes of models, like even the original DeepSeek paper, they talk about small models needing more cold start SFT before they do RL and stuff. So there, like we've seen some plots of this, but I think your intuitions kind of hold, right? Like RL works on different things on different models at different sizes. And for other stuff, you can do more mid training and stuff, but you kind of, that's like why mid training exists too, right? Like this field kind of came out of, if I want domain specific reasoning models for something, like all these material science companies, they're taking small to medium models, doing mid training on domain specific data, then doing RL, and that helps them there. And there's like, I have some friends working on this and they've tried plotting scaling law curves of what size models they can use. So, like at periodic labs, my friend works on mid training and he's tried this, so like for the Quen family across all different models, they do mid training before their RL, then they eval them, and their model size actually doesn't make too much of a difference, but they're also not using the smallest models. It's not something they're super optimizing on, but like they did test it, but they're not really compute constrained to not use a big model. But it's a cool paper. You should cover it if anyone wants to volunteer for papers. It's that time. We have someone next week doing an Omni model, I believe. Let me pull up the paper. And then if anyone wants to volunteer for papers following that, we talked through like 6 or 7 other ones today. If there's any volunteers, the week after next or any other following weeks, feel free to, claim a spot now. Otherwise, I think we're quite a bit over and we should call it soon.
Question, was the egg roll paper ever covered?
I don't think so.
Yeah, okay.
Wait.
I'll do it at some point,
The what paper?
either in 2 or 3 weeks. The egg roll one. It's a new way of training models that doesn't use backpropagation. It's a very cool paper.
What? No
Yeah,
backprop?
no, but it's actually mind blowing. It uses evolution
It's
strategies
it's
to train.
titled very differently. It's not called egg roll paper. It's like evolution strategies. But
Oh yeah,
their
that's very
method
true.
is egg roll. Egg roll is an acronym like
Yeah,
evolution guided stuff or whatever.
yeah.
Okay.
Cool.
Amazing.
Okay, we have egg roll soon.
Egg rolls, egg drop.
Egg drop.
Okay.
Cool.
Thank you
Thanks,
All right,
all.
guys.
thank you,
Merry
everyone.
Thank you, Frankie.
Christmas.
everyone. Thank you,
Bye-bye.
Thanks,
Frankie.
listeners. Thank you, Frankie. That was great. Come back soon.